If neutrons are disappearing, then maybe they're disappearing into an alternate parallel universe. Sounds crazy, but this is actual physics that people are testing. Imagine how different the world could be if parallel realities were not just confined to the realms of fiction. Would we be jumping between multiple dimensions like hopping on a train to go from one state to another? Do you think of each choice that you make possibly changing everything about the world that you exist in? It's not that your choices create different universes. Different universes get created and maybe you're different in them. Well, the concept of different dimensions existing might not be fictional after all. CERN has just made a shocking discovery about the possibility of opening a portal to another dimension. How will this affect us? Is it even viable? Most importantly, are there any consequences to meddling with the fabric of space and time? Join us as we dive into CERN's spooky yet fascinating research. The role of CERN. To get to the bottom of the whole deal with portals, dimensions, and particles, we first need to understand what CERN is and what it does. CERN, also known as the European Organization for Nuclear Research, is the product of scientific imagination nestled in the heart of Europe. This research facility has been in the picturesque countryside between the French and Swiss borders since the 1950s. Representatives from 12 European nations gathered in Paris to lay CERN's foundation with one goal in mind: creating a center for nuclear research that would propel Europe to the forefront of scientific discovery. Over the years, CERN has made significant contributions to the world, namely the World Wide Web in 1989 and the Large Hadron Collider LHC in 2008. The LHC was the world's most powerful particle accelerator yet, buried deep beneath the Earth, spanning over 17 miles in circumference with equipment such as magnets, detectors, and experimental apparatus inside. The main point of CERN is to help us understand the universe around us in detail, and they do this by examining the smallest constituents of the universe: particles. With an array of particle accelerators and other machinery at their disposal, they plan to dig deep into fundamental physics. One such example of that machinery is the Large Hadron Collider, as mentioned before, which is relevant to the topic of different dimensions yet to be explored. The Large Hadron Collider and the particle collision process. So, what is the Large Hadron Collider? Well, the LHC is the world's largest and highest energy particle collider. This spectacle of engineering is so awe-inspiring because it was built by the efforts of over 10,000 scientists and hundreds of universities, as well as laboratories. It is hidden from sight at a depth of 175 meters, 574 feet, within the Earth's surface and lies in a 27 kilometers tunnel near Geneva. The first collisions from the Large Hadron Collider were achieved at an energy of 3.5 tera-electron-volts (TeV) per beam in 2010. This amount of energy was worth noting because it was about 4 times the previous world record. However, the LHC has been shut down quite a few times for repairs and upgrades, namely between 2013 and 2015, and later in 2018, after which it was opened back up in April 2022. These frequent shutdowns resulted in the upgradation of the LHC from 3.5 TeV to 6.5 TeV per beam, keeping up with its status as a powerful particle accelerator and collider. 9 detectors and 4 crossing points allow the LHC to perform at the top of its game, detecting different phenomena around the crossing points. However, why are they even doing this? What need do we have to collide with particles and ions? Well, the goal is to get answers to various questions. Where are the families of new particles predicted by supersymmetric theories? What do the particles do when they collide with each other at different speeds? How about the speed of light? What if there are new particles whose existence we are completely unaware of? All these unresolved questions in particle physics are the reason why we built a facility as large as CERN in the first place. That brings us to the fascinating process of particle collision, something that has brought us infinitely closer to the possibility of other dimensions. The process of particle collision is quite possibly the simplest possible approach to studying the most fundamental pieces of our universe. In simple terms, we use such big machines to smash things together and see what happens. A very Neanderthal approach indeed, but it works. However, what sets us apart from Neanderthals is our tools and our approach. Instead of rocks and bones, we have accelerators that can make the particle speed approach the speed of light. In this multi-step process, The LHC consists of radio frequencies that accelerate charged particles to nearly the speed of light. With it, they have superconducting magnets to maintain the circular orbit of these particles as their speed dramatically reaches 0.99999 times the speed of light, only 3 meters per second shy of being the actual speed of light. The very first step is to inject the particles into something called a linear accelerator or LINAC. What it does is that it charges the particle to reach speeds of approximately 50 million electron volts. Then they are inserted into the circular accelerators, which gradually increase the energy of the particles to several trillion electron volts, TeV. Some of these circular accelerators include the proton synchrotron booster, the proton synchrotron, as well as the superproton synchrotron. Finally, the two main rings of the LHC, 27 kilometers apart in circumference and 71.316666 magnetic fields, energize the particles up to 7 TeV, and then the particles collide head-on from opposite directions. These high-energy collisions result in us noting some interesting things about the particles, whether it is new particles being formed or a blast of energy being released. These observations help us get closer and closer to understanding the universe around us. These collisions produce a wide array of particles, some that have never been seen before by any laboratory. How are these tiny particles observed? The detectors put in different places inside the collider track the paths of the charged particles and measure their energies, momentum, and type. Analyzing these particle production patterns allows us to determine the properties of the detected particles and make further observations about their behavior. A question might arise in your mind: how do the particles in the LHC not miss each other during this particle collision process? With a size so small, how do they move with such accuracy? Upon keen observation, it is noted that the particles in the LHC are bundled in needle-like packets and then squeezed to reach the collision point. Each needle-like packet is said to contain about 10 to the power of 11 protons, with only a handful of collisions each time the two packets collide. Due to the frequent collisions, they can add up to billions per day. However, as marvelous as this creation is, there have been quite a few concerns about the LHC ever since it was created. The concerns about the Large Hadron Collider have been around for a long time, almost since the birth of the facility. Since its early stages, concerns about accidentally creating a black hole were raised, hypothesizing that it could devour our world. Recent discoveries by the Large Hadron Collider have not stopped the clock of innovation and research, leading it to discover some amazing things. For example, physicists detected a mysterious primordial particle known as the X particle in early 2022. More specifically, it was X3872, first discovered in 2003 by the Japan-originated Bell experiment. In this experiment, the particle collider smashed together high-energy electrons and positrons to form the mysterious X particle, but they ended up decaying too quickly for any detailed examination. It was then proposed that X3872 would be better illuminated in quark-gluon plasma. Cut to 2022, about 100 of these X particles were detected inside a broth of quark-gluon plasma by smashing together lead ions. These particles were theorized to exist near the Big Bang for a very brief period of time. These findings were published on January 19 in the journal Physical Review Letters. Did you know that what we see in space, like planets, stars, and galaxies, is just a tiny part of the whole picture? In fact, it comes up to only about 4% of what's out there. What really defines the universe isn't so much the things we can see, but the empty space around them. Scientists have discovered that most of the universe is made up of things we can't see directly. These invisible substances don't emit light or any other kind of radiation that telescopes can detect. Instead, we can only detect them because of the way they affect the movement of stars and galaxies through gravity. We call these mysterious substances dark matter and dark energy. We're still not sure exactly what they are or how they've shaped the universe, but they open up exciting possibilities for discoveries in physics. Dark matter makes up about 23% of the universe. We first suspected its existence back in 1933 when we noticed that the way galaxies move suggested there was more stuff out there than we could see. We cannot directly see or interact with dark matter, but there are ways around this problem. Dark matter can be described as a murderer running away from a crime scene. The physicists survey the crime scene for bloody footsteps, and these footprints give us hints and clues about how much of it is out there. So, what could dark matter be made of? One idea is that it might be made of supersymmetric particles. These particles are like hidden partners to the particles we already know about, symmetrical yet opposite. Scientists are trying to find these particles in experiments like the ones happening at the Large Hadron Collider. Now, let's talk about dark energy. Dark energy makes up about 73% of the universe, making it one of the most important characters in the cosmic theater. Dark energy seems to be responsible for a surprising observation made in the 1990s. The expansion of the universe is speeding up. This was a big surprise because scientists had thought the universe's expansion would slow down over time due to gravity. Instead, it seems like something is pushing the universe apart. Scientists called this mysterious force dark energy. They think it might be related to a force called the cosmological constant, which Albert Einstein once suggested might exist. One of the ways scientists study dark energy is by looking at how galaxies are spread out across the universe. They look at the light from supernovae, which are exploding stars. Supernovae are so bright that they can be seen from very far away, and they act as cosmic landmarks. By measuring how the light from the supernovae is stretched out over time, scientists can figure out how fast the universe has been expanding. Another idea is that dark energy might be a new kind of energy field that fills space. We still don't fully understand what dark energy is, but studying it might help us understand the fate of the universe. Will the universe keep expanding forever, or will it eventually stop? Dark energy holds the key to this cosmic mystery. CERN's discovery. So, how does CERN come into play? It turns out CERN has been observing some strange behavior in neutrons, one of the building blocks of atoms. In certain experiments, neutrons seem to be disappearing and reappearing like magic, but scientists think there might be a scientific explanation. The neutrons might be slipping into a parallel universe. This idea is based on a theory that our universe might be just one of many, like bubbles in a cosmic bubble bath. If this is true, there could be other dimensions out there that we can't see. Scientists at CERN are now designing experiments to test this idea. They're trying to create conditions where neutrons might slip into another dimension. If they succeed, it would be a huge breakthrough in our understanding of the universe. If CERN really can open a portal to another dimension, it would change everything we know about science. It could help us understand dark matter, dark energy, and the true nature of reality. This discovery would be like finding a hidden door to a new world full of possibilities and new knowledge. We might discover new particles, new forces of nature, or even new ways to travel through space and time. CERN's quest to unlock the secrets of the universe by potentially opening a portal to another dimension is a groundbreaking endeavor. This journey into the unknown promises to unravel the mysteries of dark matter and dark energy and redefine our understanding of reality. The implications of such a discovery are vast, offering a glimpse into parallel universes and new dimensions that could revolutionize science, technology, and our perception of existence itself. As CERN continues its pioneering research, we stand on the precipice of an era of unprecedented exploration and discovery, heralding a new age of cosmic understanding. The potential ramifications of CERN's research extend beyond theoretical physics into realms of practical application that could redefine human understanding and capabilities. Imagine if we could harness the insights gained from probing alternate dimensions. Such knowledge could revolutionize technologies ranging from quantum computing to energy generation and propulsion systems. By delving into the fabric of space-time itself, CERN not only seeks to uncover the secrets of dark matter and dark energy, but also aims to unveil new laws of physics that could lead to paradigm-shifting advancements. Moreover, the exploration of parallel universes opens up philosophical questions about the nature of reality and our place within it. If alternate dimensions exist where different physical constants apply, what does that imply about our own existence? Could it suggest that the universe we perceive is just one iteration among many possible configurations? These inquiries are not just academic. They challenge fundamental assumptions about our understanding of existence and could reshape entire fields of philosophy and theology. Furthermore, the technological implications are staggering. From developing new materials with properties unimaginable in our universe to potentially accessing vast reservoirs of energy from alternate dimensions, the practical applications of such discoveries could be limitless. While the path forward is fraught with scientific and ethical considerations, CERN's pursuit of knowledge stands at the forefront of human curiosity and ambition. As we look to the future, CERN's ongoing experiments may reveal insights that fundamentally alter our understanding of reality and our place within the cosmos. The quest to unlock the mysteries of parallel dimensions promises not just to expand scientific knowledge, but to redefine what is possible for humanity in the vast expanse of the universe.